Hello, folks. Welcome to our fifth lesson on work, energy, power, and machines. Okay, so today we are going to have a full lesson on how to solve problems. Okay, so let me take you to my laptop so that we can focus on what I have prepared for you. We still are continuing with the work, energy, power, and machines. Okay, so you have my Gmail there in case of any problem. So let us look at a scenario 1. Calculate the work done by a mason lifting a stone of mass 15 through a height of 2. I think I had introduced this. So since it is a continuation of my work, you can just try it on your own. Then I think I did also number 2. Okay, number 2, I also think I did that. I'm sure my camera is focused. I want to get you focus. Yes, so I think I also did that. A girl of mass 50 kg running up, and the first thing that you have to remember is to sort out. You see, I'm sorting out. I'm writing what has been given. I'm given mass is 50. This topic deals a lot with the force and the distance. Okay, and then you have the energy change is the same as work done. So from mass, I'm able to go step by step to get force. Force due to mass is given by the formula mg, and then you get the real force here. And then you have the distance, which has been given in centimeter. You get the total heights of the steps. Then division by 100 is to convert. Okay, I've converted. So work done can be easily found. So let me start with the number 3. We continue. A force of 7.5 Newton stretches a certain spring by 5 centimeter. How much work is done in stretching this spring by 8 centimeter? As usual, sort out. You can see bullet 1, bullet 2, I'm sorting out. And I want you to be systematic in your work. You know, we have a stretch of 5 and we have a stretch of 8. The core question revolves around the force that caused a stretch of 8 centimeters. Because the force that caused a stretch of 5 centimeters is given as 7.5. So I have sorted out in 2 lines to help you know there are 2 parts in one question. So the force F1, which is given, caused an extension of 5 centimeters, and I've done conversion of centimeter to meters. The second scenario, we need a force 2. It is the force 2 which will help us get the work done on that spring which was stretched by 8 centimeters. So you have to sort out your work. After sorting out your work, you go to the knowledge. As I said, knowledge is just a formula, a correct formula that is to be applied. Okay? So I've given you a push in bullet 3. A force of 7.5 produces an extension of 5 centimeters. We need to know a force that will cause a stretch of 8 centimeters. When you do that, you get 12, then you apply that. So these ones, go through them again. Okay, go through them, see the approach. You can have that. Now let us move on to example. Let me put it up there. This is example. I want to dwell on also. You have the normal lifting, I've shown you. You have the second question or application you are exposed to is about springs. You are getting that. Okay, now we are getting a motion. You see, all these are different scenarios. Motion. So a car traveling at a speed of 72 kilometers per hour is uniformly retarded by an application of brakes. So when you apply brakes, the vehicle does not accelerate. Its speed or its velocity reduces. A reducing velocity is also known as retardation, and that takes place in 8 seconds. So what are we talking about here? A vehicle is moving and then it is made to stop by a particular force. Okay? If the car with its occupants has a mass of that, calculate the braking force. So this is a kind of linear motion brought in, and we can do it in a very simple way. So let us address part A. Again, see the way I start, sort out, so that you are clear which quantities are given. These quantities are the ones which will break the formula. So U is 72 km per hour converted to 20 meters per second. How do you convert? You remember 72, in short, you can multiply by 10 over 36. Okay? Remind yourself, how do you convert kilometer to meters and then hours to second? You will get it. The simplest multiplying factor will be 5 over 18. So normally, you have your own shortcut. Whatever I'm given, I multiply by 10 over 36, which in a sense is the same as 5 over 18. So I chose 10 over 36 because I know 36 goes into 72 2 times. So 2 times 10, 20. Final velocity, because this car is going to stop. So we have V is equal to 0. And what time did it take? 8 seconds. Now, from that formula, from that sorting, we go into knowledge. The knowledge required here is braking force. Braking force is equal to mass times acceleration. So I have to know acceleration because the mass is already given. And therefore, it calls for the formula V is equal to U plus AT. V is equal to U plus AT. Okay? That formula will give me an acceleration of negative 2.5 meters per second. So in physics, what does that negative stands for? That negative stands for retardation or deceleration. Velocity change reducing. Velocity change reducing. You are from a high figure, you are coming to a low figure. Okay? So, retardation. If I write retardation, I don't put negative because you will be doing physics that is not known in the world. If I write retardation, I don't write negative. Why? Retardation already tells me it is negative. The figure I'm talking about is negative. Therefore, I come to the major formula. Braking force is equal to, substitute, F is equal to MA. So M 1250, A 2.5. You get braking force is equal to 3,125 Newton. Okay, that is braking force. So if you did not write braking force, and you had just F. You had just quoted F is equal to MA. Your substitution will be F is equal to 1250 times negative 2.5. So your answer will have a negative 3,125. That negative means breaking force, because not all forces are breaking. Okay, force is a vector quantity, it has a direction. Now let us address second part, the work done in bringing it to rest. I am doing it from energy change point of view, and I will like you to do it from work is equal to force times distance. So this is what you should do. You will do it from work done is force times distance. Distance you will get using the equations of linear motion. You multiply by force and then you see what you will get. Okay, because you have already breaking force. You have already breaking force. So I want you to do work done is equal to force times distance. Get S from the equations of linear motion. Me, I'm showing you that I can get it from energy change. Okay, so work done is equal to kinetic energy lost by the car. Now we say lost is technically, I should put what those things in English. You should put something here. Lost is not lost. You put something here and something here. It's not lost. If you are told to account for this lost in quotes, it will be converted to heat energy and maybe sound. So we are using loss because of it not being seen, but it has changed from one form to another. So how do you handle it? I'll get the final kinetic energy minus initial kinetic energy. Kinetic energy is a half mv squared. V is 0 and U is 20. So you will get that is the work done. Okay, the work done is equal to kinetic energy lost or kinetic energy change, because you can see there is a minus. There is kinetic energy 1 minus kinetic energy 2. We can also say kinetic energy change. We can say kinetic energy lost, but lost in quotes. It is not lost, it is changed from one form to another. Okay, I hope you have understood that. And let me now address another scenario. I've exposed you before in springs. Okay, we started with a simple thing that you can lift a body, gravitational potential energy. You can lift a body, you can push a body. Those are direct scenarios in life. Then you had a spring. I showed you whenever you apply force, a spring stretches, and when you plot a graph of force against extension, you get a linear graph passing through the origin. Area under graph is a half base times height. Our base is extension, our height is force, and you get the work done, because you are basically dealing with force times distance in the name of extension. Then you have also had a scenario of the motion, vehicles moving. So this is just to kind of ice everything. A spring that has a spring constant of K, 100 Newton per meter, is stretched to a distance of 20 centimeter. Calculate the work done by the spring. Okay? We know work done is force times distance. what I'm stressing more is that when you plot a graph of force times distance or extension, a graph of force times extension, the gradient gives you spring constant. That is division, vertical quantity divided by horizontal quantity. But when you take a vertical quantity multiply by horizontal quantity, you come up with the area of a triangle, which is basically a half base times height, or a half FE. But you know F is equal to KE. Therefore, you can have a half KE squared. So when you sort the information, when you sort this information, what is given, it is the one which brings you to the knowledge. The knowledge brings you to substitution. Substitution brings you to the final answer with the correct units. Okay? As I finish, sort out your work. Any question you are told to calculate, basically it is answered by a formula. So what do? Sort out the units, the quantities and the correct units given. Then identify the formula, which I call the knowledge. Then you substitute and compute. To substitute is to remove letters, put the figures that are given. Then you may cancel. That is what I call computing. Your effort to try and simplify those figures is computation. Then come up with the final answer with the correct units. Those will earn you marks and you will be sure of being a better teacher than me. Till then, boys and girls, I say bye-bye. That is the end of this lesson. Next lesson, lesson 6, I'll deal with the power. Remember, we still have a lot. When we deal with the machines, that's when you will see it is deep. Bye-bye.